Hello, everyone. My name is Sherry. So, as you can tell, this is the boat that we built. So, about 3 years ago, my friends and I realized that. So, we were talking to some water authorities, and they were telling us that they need a better solution for monitoring water quality. So, as a bunch of hardware engineers, we attempted to automate that. That's how SS MAPR, fancy name, was born, to unmuddy the water. So I'd like to preface my talk by introducing my lovely teammates. We're a team of 6 with mixed backgrounds from mechanical engineering, electrical engineering to computer science. The project wouldn't have been possible without the support from the University of Pennsylvania and our 3 amazing advisors. I'd also like to tell our story using this V diagram. Some of you might have seen this from some systems engineering lectures. So this diagram shows the typical flow of building a complex system by starting from concept definition to requirements, architecture, to detailed design of subsystems. So everything from 3 to 5 is subsystems land. You design everything individually, implement them, test them, and then go back to the system verification, and then go back to operations. So looking back, our journey was mostly guided by this diagram, well, sort of, because the couple times we messed up, we learned it the hard way and came back to this diagram. So let's start with the problem that we're trying to solve. So Philadelphia, the city where UPenn was located, was part of the Delaware River system. But it was famous, but not for a good reason. It was famous for its water quality problems in the last few years. So many facilities have been polluting the river for many years, but it took the water departments 6 years to collect enough data to regulate their emissions. And 6 years, well, was enough to seriously damage the local ecosystem and get many people sick. So we asked how to make this process more efficient. So if we look at how they regulate those emitters, they need an accurate aquatic model to facilitate the regulation process. And the bottleneck back then was that it took them years just to do the first step, to collect enough data for to sample and measure and get the data, to model, and then propose a regulation. And that took time. So currently, what they do is that they took measurements at fixed locations along the river, and they also took samples at the surface. So this data point is super limited. One sample was used to represent 6 miles of river, which is on average 45 feet deep. What does it mean? It means like we're trying to predict whether there's gold 3 floors underground in downtown LA by taking a soil sample in Pasadena. So to solve this problem, they have tried doing some multi-depth measurements by hand, like in this photo, but unfortunately it was very expensive, so they could only do this once a year. So we talked to multiple water departments, and we started to hear the same thing. The river is so big, and it changes so dynamically that it's very hard to keep up with this change over time. And because of this, more data, more frequent data, especially multi-depth data, will be very valuable to them. And this problem wasn't limited to water departments too. Aquaculture companies said the same thing about their fish farms right here. So we actually looked around and we found some autonomous multi-depth measurement solutions out there, like this fancy autonomous surface vehicle and this even fancier autonomous underwater vehicle. But their problem is pretty obvious. They're very expensive. And also, this is like from our insiders, the boat could collect 1 liter of water, but for the water departments, they need a lot more water to get the number of metrics that they want from the water samples. So for our prototype, we decided to focus on a cheaper and denser spatial data solution. Specifically, we'll build a solution for multi-depth measurements and samples to help water authorities monitor pollution, salt front, and bacterial composition for regulatory purposes. And we would also hope that this will be used by fish farms to improve their fish farming environment. So here are requirements. An ideal solution should cost less than $3,000 upfront. It should take at most 4 hours to run, which is about half of a workday for our regulators. And it should be able to get a cross-sectional map for a typical cross-section along the Delaware River, which is about this wide and this deep. And it should get 8 liters of volume. That's what they're asking for. And it should only take 1 person to run. So these requirements conclude our first step of the V diagram. Later on, they proved to be very crucial to enable us to finish the project in actually 6 months, because we could design and implement those subsystems in parallel and validate the success very quickly on our own. So now that we have a problem to solve, let's get into the high-level architecture. So what would the solution even look like? Well, after some initial brainstorming, we came down to 4 options: a submarine, a drone, a crawler, or a boat. So we ruled out the submarine solution very quickly, as the price exceeds more than 50 times our budget. And then we looked into power consumption and how many number of trips is needed to collect 8 liters of samples. And drones just won't work because they're super limited by the amount of weight they can carry. And if we're limited by weight, why don't we just develop something that crawls underwater on the ground? So we came up with this underwater crawler with a little buoy on top. And we quickly realized that the Delaware River is just not a good place for this boat because it's known for its large amounts of silt buildup and vegetation, and the crawler will just get entangled at the bottom very quickly. So this leaves us with the last form, which is a boat, and this is when SS MAPR was born. So here's a breakdown of the 3 subsystems on the boat. We have the first one, task functions, that include sampling the water, getting it on the boat and collect them, and also measuring the water quality metrics in the water. And the second one, pretty simple, drives the boat. It has an autonomy software and a control mechanism. And the third one includes UI and data processing, which communicates with the onshore machine laptop. And there's also a power subsystem that provides energy for all the moving parts on the boat. For the task function, so here's a high-level design. We'll get into all of the details, but essentially a long tube is lowered to collect the water, and the water will, so that's the, I guess, the sampling mechanism. And then there's a probe here, so that's the measuring. And then the water is sucked up, so fancy animation, yes. It's sucked up to the boat and then go into one of those sampling bottles, so that's the sampling. And then lastly, we also have a collection, which is like this tray will rotate itself to fill up the sampling bottles, and we take them back to the lab. So for the actuation system, this is a slightly more detailed view of what it looks like. So we designed 2 control modes, manual and autonomous. In either mode, the control signal is sent by the user from the onshore, as you can tell, it's a laptop, through XP to a Raspberry Pi on the boat. And the Pi controls the propellers actually through another microcontroller to the propellers, yes. So for manual control, the control command is just directly relayed. There's no extra processing, but for the autonomous mode, we actually just ask the user to put in waypoints, and then the Raspberry Pi will calculate the thrust needed based on extra IMU and GPS data. We'll get into more details, but this is just a high-level overview. So putting everything together, this is what it looks like, much prettier in the CAD. We're going to build a low-cost autonomous boat for multi-depth water quality measuring and sampling. Guess I'm kind of on time. All right, so we tackled the design details actually per subsystem after we did the whole high-level design and whatever. So let's first take a look at the task functions. And to start off, how do we get the water from the river up to the boat? So that's the sampling. So how did we design this? So according to the users, we have at most 4 hours to collect samples at 10 points across the river and up to 10 locations downward into the river. So that's a 100-point cross-sectional map for measuring and sampling. So our boat should be able to navigate, so there should be enough time to do these things. And then second, our boat should navigate at a speed higher than the worst case river current speed, which was measured at about the speed. And after some quick math, we allocated 47 minutes for travel and gives us 190-ish minutes for the task functions. So these time constraints helped us narrow down like how to design the pumping mechanism. So this is an example decision we made, which is how big is the tube, right? So as shown in this plot, the flow rate in the tube goes up with the tube diameter. So we consider several factors. First, the flow rate cannot be too slow, and friction, which also cannot be too slow. And then lastly, if you get too big, there's a space constraint on the boat. So we basically like kind of draw out this small feasible window, and then we picked a tube with 5/8 of inch inner diameter, and this also helped us get the flow rate, which helped us pick the pump later on. So that's one thing we did, and then oh, cool. So that's the pumping mechanism. That's like the major design decision there. And then we had to test it. So what we did was, we didn't have the boat yet at that point. So we set up the system in a building, in a stairwell. And we put the whole pumping mechanism on the 3rd floor. And we put the water on the 1st floor. actually on the basement. And then our goal is to say that, hey, can we collect 10 bottles of water by pumping water from the basement to the third floor in the time limit that we want. So it turns out that we could. So here are the results. We did some theoretical measurements before we did the experiment, and then like this is like the amount of time that it should take per bottle, like based on this depth. And then the orange points were the measured points. And it turns out we were pretty close to the expected values, and it took us under 6 minutes to collect the 10 water samples within a column. So this is much better than the 19 minutes that we're aiming for. And this leaves us a lot of buffer for some other cleaning and positioning the sample bottles later on. Cool, so, oh yeah, we have some buffer. And second, let's talk about I mentioned that we had a probe at the end of the tube. So that's our measuring mechanism. So a very important component of the measuring system is to ensure that the probe stays within a 1 meter cubed box as required. Otherwise, you're measuring from a different depth. So what it looks like, so when you have a current, it will push it away from the bounding box, right? So essentially, we had to minimize both the vertical and the horizontal error. To minimize the vertical error, that was simple. We just added a depth sensor, and we control the tube length to just keep it within this vertical bounding box. But for the horizontal error, we had to decrease the angle theta, this theta here, by making this thing heavier. So we added a sounding weight. So how did we do this? We plotted the angle theta we saw just now as a relationship to the weight of the sounding weight, and then we plotted against the current speed for up to 2.5 miles per hour. And then from this plot, we can ask the user to just select a sounding weight based on the current speed on that day to keep the theta lower than the threshold. And here we are. Cool. So another challenge we had was to maintain the data quality from the depth sensor. So actually, when we did the experiment in the lab, everything was great. The wire is short, the quality is high. Okay, not too high, but it's reasonable. But as we increased the wire to 50 feet, this is the data we got. It didn't work. So for this reason, we added a boosting and a filtering circuit to maintain the data transmission quality so that we can keep the depth sensor accuracy at the 2 millimeter as claimed by the manufacturer. So these are the main things that we tackled at the end of this stage. We validated the 3 task functions in the Schuylkill River in Philadelphia, the smaller river right next to Delaware River. And as you can see, so this video is a little hard to see, but essentially we lowered the pump right here, and we were pumping away the water from the tube from a different depth first, and then we moved it to bottle 2. And then we were pumping water into the bottle at this time. And then after that was done, it was moved back to the exhaust. So that was like the process of one sample. So we did 10 bottles at that configuration, essentially. And then the second thing that we did was measuring, right? So this is actually a data that we collected later on of a autonomous boat run. So basically the probe was lowered to 10 points across the river, into the river, and then we get a conductivity map. And that was very similar to the one that they usually collect, but usually they only collect a couple of data points, but now this is a full map. So yeah, this is a task function. So now let's get into the second subsystem, actuation and control. So one of the most important, can I stop this? Stop this. One of the most important parameters that guided the design for that control was the coefficient of drag, which is CD right here. So we first get a theoretical value through a fancy simulation called computational fluid dynamics in SolidWorks. And then this value was confirmed through a pool test. So this was our school swimming pool. And we basically drove the boat through very simple PWM control until it reaches constant speed, and then we measure its speed. And then we use this to match up the PWM values and the speed. And then from the data, we calculate another CD. And then we found that it was pretty close to our theoretical value. So we basically used the measured one for simulation and also for selecting a propeller. So a second thing that we did here is to select a processor. I don't know how much was there to say, but this is what we selected. We chose Raspberry Pi as the main processor, considering its computing power was enough for the autonomous navigation software we're going to run, and it's cheap, and it doesn't require too much power to power. And then to complement that, we added a microcontroller to control the motors. Two big reasons. One is Raspberry Pi just simply doesn't have enough PWM ports, so we had to need a second one. And then it also helped us separate the low-level control loop from the heavier computations that's happening on Raspberry Pi. And we picked MBAT because of its good library support, and it's very customizable because it's C++. And most importantly, as what you usually do when you pick a board, is some of us have used it before. So we know how to use it, and we know how to debug it. So yeah, this is, I guess, like how the software was laid out across the two boards. The main computer gets the computation-heavy tasks like autonomous navigation, the RF communication, and like a big, giant state machine for the task functions and data processing. And the microcontroller takes off the low-level control for the propellers, the motors, the pumps and valves, and getting data from the measuring probe. And these two boards are connected through a simple serial connection. And the main advantage is that by separating the high-level state machine and the low-level control loop, we can ensure a very low latency planning loop that's constantly talking to the user control onshore without compromising the control frequency. Cool. So for those of you who are interested in what autonomy that we used, we implemented a localization algorithm with a filter called common filter. It has two update stages, and it chunks out a location of the boat. And the first stage, the action update, it takes in IMU data and then does some math, has an action update. And then for every GPS input, it has a measurement update. And then so by doing all those like math that's going on in there, it basically accounts for the uncertainty in both of the sensor updates and then fuse them together to give us a slightly more accurate location information. Yes. So that's the localization. And for the control, we just use a simple PID control. But in order for the boat to switch naturally between like following a path and stopping, we actually designed a state machine with 3 different control modes. One is turning, just simple turning. And one is heading towards the next waypoint. And one is staying within the bounding box. And within each mode, it's a simple PID controller. It takes in the error of the boat's distance and the angle. And calculates the thrust needed for the 2 motions. So yeah, so here's the fun part. We are testing the control performance on the river. So here in this experiment, we confirmed the accuracy of the localization algorithm. So the boat was driven in a straight line, and we derived the trajectory from a drone video. And then we plotted the raw GPS data, which has a range of 5 meters. But after we like pass it through the Kalman filter, it got down to 1 meter. And this was like good enough for our precision for the control. And then the other thing that we tested was that can it hold itself in the same place while it's doing the sampling and measuring? So we placed the boat at 3 different locations in autonomy mode for 20 minutes, and then again derived the trajectory from drone videos and plot them against the bounding circles and validated that yes, it can hold itself within the 2-meter radius that we asked for. And last but not least, we tested its ability to follow a set of waypoints. So in this plot, we actually showed both the simulation results and the actual results. And the drone video was kind of like matches it up, but I don't think it's the same run. But essentially in simulation, we tuned the parameters with a probabilistic sensor input. And then during testing, we asked it to follow the same waypoints and see whether like the performance was close enough as what we thought it would do. And this actually confirms our simulation results pretty well. And most importantly, it was able to hold itself at the spot that we asked it to hold at. Cool. So lastly, I guess a few brief words on what we did on the power. So for the power source, we added up the power needs of all the components and did a down selection again. And to balance between cost and weight, we ended up deciding on a gasoline generator. So there's actually a pretty dramatic story here on why we decided a gasoline generator, which we'll get into later. But that's all you need to know for now. Cool. So let's look at what SS MAPR would look like for a user. That's an ideal user flow that we took a video. Let's say Joe, one of our main contacts from the United States Geological Survey, is going to collect data and samples from the Delaware River. He arrives on site in his very typical pickup truck, not from U-Haul, and with the help from the driver, he unloads SS MAPR and takes it to the dock. And then he turns on the gasoline generator on SS MAPR, and then he also pumps up the boat. Yes, and then on the user interface, he can input the waypoints and the depth that he wants to sample and measure from, and blah, blah, blah. This is a simple UI, and then boom, off it goes. Cool. So SS MAPR is running in the water. Joe can follow SS MAPR's progress through the interface with live data streaming in. And if anything happens, he can switch to manual control from the user interface. So in 4 hours, SS MAPR drives back with 100 data points, 2.5 liters of samples, and he packs up and goes back to the office, and that's half a day of work. So full disclaimer, we didn't actually implement the UI and the real-time data processing at the end, but this is an ideal user flow that we used for pitching this to teachers. All right, so this is what we end up achieving. We end up getting a fixed cost of about $2,800, so that's under $3,000. And then it is, of course, much cheaper than the existing other solutions. And we also achieved a much lower unit cost because SS MAPR can collect a lot of data points and a lot of water sample in one trip. One thing that we did have to mention that we didn't achieve the 41 metrics that they asked for, but we did 60, which is already a lot better than the 2 metrics that they can do. But there's still a lot to improve here. And last but not least, we reduced the manpower required per trip from 12 hours to 4 hours. So here is a close-up video from the final system test, and we're proud to say that SS MAPR helps water authorities get more data at a lower cost. Right, that's not the end yet. So here are some of our takeaways from building SS MAPR. I don't know if you still remember this diagram that I mentioned at the beginning. We actually didn't take it too seriously during the process, and we got a couple roadblocks, and it kicked us back to this diagram. So to summarize how it has helped us, first, the metrics that we designed at the beginning, the big slide with a lot of numbers, that kept us on track by providing a way to objectively measure progress and success, so we could wrap up every stage very quickly and move on to the next. And as you can tell, we use down selection throughout the design process, high-level architecture, subsystems. And then some lessons learned: always test the subsystems first before putting everything together. We learned it the hard way, and also budget a lot of time for integrating everything together because they always break when you put them together. So we actually tried putting everything together at first, something broke, and we had to take it apart and integrate them one by one at a time. And lastly, operations. So we actually found a lot of usability issues at the final systems test that we did not anticipate, such as how to organize the spool of tubes very elegantly. And to make this SS MAPR usable by everyone, there's still a long way to go. So this was the drama that I promised. So we run into many unfamiliar subjects throughout the project, and it's okay to be wrong for the first few times, as long as you keep trying. So our initial calculation for battery capacity was very wrong, and we were also spending a lot of time trying to build a battery pack because we had no idea how to build one. And as we were running out of time, some advisor was saying, hey, why don't you just use a small gas generator? We're like, sure. So we did. But we had to add a lid to keep the generator away from water, as warned by the manufacturer. And we also had to build an entire air circulation system, inlet fan, exhaust duct, to make sure that the generator can stay functional throughout the 4 hours. So here we are. This is how we built the lid with carbon fiber. And as you can tell, we were having a lot of fun. My third takeaway from this journey was that to solve environmental issues, we need a lot more hardware solutions. And my major was electrical engineering, and I did most of the software work on this project, but software was not going to help us collect more data from a muddy river, nor is it able to fix global warming. So because of this, after I started working, I started Nerva Labs with a team of roboticists and engineers with a mission to encourage more hardware engineers to build climate solutions by sharing what we've learned. Right now, we run a blog and a newsletter on impactful climate hardware solutions, and sometimes share tips on applying robotics to real-world problems. And soon we are gonna try to share some tips of climate hardware project ideas coming from industry stakeholders. So you're welcome to learn more through this link or come find me after the talk. So I'd like to thank all our advisors from the water authorities and Hackaday, Cornell Cub, University of Pennsylvania for making SS MAPR possible. And thank you for listening. Now I'm open for questions if we have time. This is SS MAPR's perspective.